My research is on studying the category of stochastic matrices through the category of convex sets. We will look at some background, some of the structure of convex sets, look at some candidate functors between categories, talk about how category theory is used to interpret logical operations, and talk about future work. Category theory is a branch of mathematics which deals with relationships between mathematical objects. A category must have objects, errors between objects, which I will refer to as morphisms, and a rule for composing morphisms. The first category is stochastic matrices, abbreviated STM. Objects are positive integers. Morphisms are stochastic matrices, and morphism composition is matrix multiplication. The other category is the category of convex sets. Objects are convex sets. Morphisms are set functions which preserve lines, and morphism composition is function composition. The category of convex sets has much richer structure than STM. Convex sets have products, which is an object, and morphisms to the original objects, which play nicely with all other objects and morphisms in the category. Convex sets also have pullbacks. These are a little more complex than products, but they ensure that some logical operations can be interpreted. There are also monomorphisms in convex sets. In category theory, monomorphisms imply equality between composed morphisms. A lemma I have proven is that in convex sets, functions are morphisms if and only if they are one-to-one. A functor maps one category into another category. They are made up of two functions, one from objects to objects and one from morphisms to morphisms. Specific structure must also be preserved. The first functor I defined is f. The object function maps the positive integer n to the unit ball in n dimensions, and the morphism function maps stochastic matrices to the linear transformations they define. This functor is nice and is easy to work with, but it does not keep enough structure from STM. Specifically, terminal objects are not preserved. Meng defined a functor between the categories, which is better. The object function maps the positive integer n to the convex set Sn, and the morphism function map is the same as in f. I used ideas from this functor to improve f. I called this new functor h. Like f, h maps positive integers to unit balls, but one dimension lower. This preserves structure, but makes the morphism function more complicated. The solution is to shift the unit ball in n dimensions into a specific hyperplane in Rn+1, and later map it back into the appropriate unit ball. This is done with a shift up and shift down functions, phi up n and phi down n. The shift up function is defined on the next slide using the shift up matrix zeta n shown here. This function moves the unit ball into a hyperplane where a stochastic matrix can transform it correctly. Zeta n lines the unit ball up with a hyperplane, and Cn translates it into the hyperplane. The shift down function is defined on the next slide using the shift down matrix omega n shown here. This function moves the new location of the unit ball in the hyperplane back into its original position in Rn. Note that the subscript for both functions describes the codomain of the function. Here is an example of interpreting a logical theory using category theory. In this example, sorts are people and the relationships are friends, and the axiom translates to any friend of A is a friend of B. For the categorical interpretation, relations are interpreted as sets, and the logical operation and is interpreted as intersection. And if the axiom is true, the left side must be a subset of the right. In the category of convex sets, instead of intersection, and is interpreted as pullbacks, and instead of subsets, the left side must be a sub-object of the right. The next steps for finishing this work are to finish proving H meets the definition of a functor. Additionally, and or need to be interpreted in SDM. We also need to find an example of a logical theory in SDM which cannot be interpreted in SDM but can be interpreted in convex sets using H. And a functor needs to be found from convex sets back into probability spaces. Here are my references.